Thanks for inviting me. And so my background is a little bit different. I come from the packaging side. And my years perked up when Andrew started talking about MCM, SIP, basically lived through all of that over the last 30 years. And that's really what I want to share with you today. I'm going to change the display. So I come from Georgia Tech, where over the last 28 years we've been working on packaging. I used to be with IBM before that, working on these multi-chip modules. So what I want to share with you is some of the things that we are working on, coming more from a system perspective, where we believe packaging is going to play a very important role. And if you think about the semiconductor industry itself, the global semiconductor industry, it's interesting that today it's a $500 billion industry. It took us 55 years to get there. And in the next 10 years, it's going to double to a $1 trillion industry. Obviously, a lot of very interesting things are going to happen. And if you follow this report by McKinsey and Company, they talk about some major drivers in this area. One is in the area of compute and storage, the second is wireless, third is automotive and things of that nature. And if you look at some of the challenges in these areas, it's pretty mind-boggling. So for example, if you look at deep learning, AlexNet and things of that nature, looking at almost a 300x brute force system scale out, basically connecting these CPUs and GPUs to be able to support larger compute power. And that's leading to an energy crisis, right? When you look at the data centers and the clouds and things like that. Similarly, on the wireless side, if you look at some of the requirements moving forward beyond 5G, once again, the amount of data you need to support is quite mind-boggling. And therefore, moving forward, I think we all agree that we need these energy-efficient solutions of the order of femtojoules per bit, supporting very large bandwidth density to be able to support a lot of these machine learning types of applications. So let me try and sort of share with you my definition of what a microelectronic system is, and why is this so important moving forward for this community. Now, all of us are familiar with transistors. In fact, all of the talks so far have been related to ICs. And if you look at the transistors today, we are at nanoscale. But if you look at the amount of volume the ICs constitute in a given system from a volumetric standpoint, it is anywhere between 10 to 20% of that system. Everything else happens outside of the IC, and that constitutes anywhere between 80 to 90% of the system. And for the longest time, if you look at the components that we were supporting on the packaging side, including the interconnects and everything else, they were at millimeter scale. So as you can see, there was a very large gap between what we could do inside of the IC and what we could do outside of the IC. And over time, that gap has shrunk. But today, if you look at the volume of a system, the reason why it's still quite large is because of the packaging part of it. So therefore, if the goal is to be able to build these miniaturized systems, clearly several things have to happen. On one side, you want these advanced devices. That's what I call as transistor scaling. These could be 3D transistors, monolithic 3D integration. But you also need the packaging side. This is what I call as package scaling, what we call as 2D heterogeneous integration, 3D stacking, and things like that. End of the day, it's all about system scaling. And the way you scale systems, especially microelectronic systems, is combining what you are able to do on the transistor side and what you are able to do on the packaging side. And that's what we call as system on package as opposed to system on a chip. So think of the most advanced ICs that you can assemble onto a package, where the package and the printed circuit board become one and the same. And you have layers in the package containing highly miniaturized components that allows you to connect between the ICs in a very seamless kind of way. Right? So this is what we call as a microelectronic system, and the rest of the talk is going to be centered around this. Now, we all know why this heterogeneous integration is becoming very, very important. Part of the reason is if you go to a lot of these advanced technology nodes, yield is becoming a problem. So when you're trying to use very large ICs coming from advanced technology nodes, cost is becoming prohibitive. So there's a lot of talk about disaggregating some of these ICs, reaggregating them using the package. And there are other reasons as well. Now, if you look at the industry, you're racing ahead in this area, right? So, for example, if you look at AMD and Intel, they have this silicon bridge technology that allows them to literally brickball these chips right next to each other using interconnects that can connect these chips to each other. And then, of course, you have the 4OS technology, the 3D technology from Intel, where you can begin to stack chips on top of each other using microchips. And if you look at the latest announcement from Intel, the Ponte Vecchio, they talk about 47 dielects on a package. And the way they count their transistors is not the number of transistors within an IC, but at the package level. And that's close to 100 billion transistors. Right? So if you look at it from an academic standpoint, the question you have to ask yourself is, in the area of heterogeneous integration, if the industry is moving forward so fast, what should the role of academia be? And that's what I've tried to capture over here. Okay, and I'll sort of put things in context here. So there are three major areas, we believe, where academia could play a very, very important role, working very closely with the industry. One is in the area of monolithic 3D integration. Now, this is not about the frontline transistors. It is about integrating transistors in the back end of the line to be able to get performance from the back end of the line as much as you would get from the front end of the line transistors. So that's what is shown as number one. The second is your ability to stack transistors, ICs on top of each other. A couple of ways to do it. One is through this wafer-to-wafer bonding. The second is the die-to-wafer bonding. We call this as reconstitution of the wafers. And the idea here is you don't have to stick to just silicon and silicon dioxide as the dielectric. There are other materials you can introduce by reconstituting these wafers, where each block that you see represents a chiplet. And then you begin to stack, and if you look at the density of interconnects you have between two layers of that stack, you're talking about millions. You're looking at an interconnect pitch of the order of 1 micron or less. And the third is being able to embed dies in the package itself. This is something that I work on personally. And the idea here is, why use TSVs to create that vertical connectivity? But there are other ways by which you can do that and get similar kind of a performance, as well as similar kind of a pitch. And the idea here is, create these chiplets and then embed them into the package and create the vertical connectivity between the chips on top of the package with the chips that are embedded in that package. Right? So we believe that when it comes to heterogeneous integration, it's all about being able to connect these chiplets with each other at a very, very high density that uses a combination of what we call as monolithic 3D integration, as well as this polylithic chiplet integration. And this is something we've started working on. And in fact, some of you in academia probably are aware of these JUMP 2.0 centers. There are 7 of them that recently got announced. And one of them is the center called CHIMES. It stands for Center for Heterogeneous Integration of Microelectronic Systems, where we're going to basically be doing this. And it's a partnership between academia, industry, and the government, basically, DARPA. Now, if you look at some of the areas that we need to focus on, right? So one of them, shown here as arrow number 2, is on the design tools and CAD innovations. And that's where I think PDA is going to play a very, very important role in terms of what we are able to do moving forward. So let's look at the EDA side of things. Let's look at how design is being done today. Now, we all know over the last 20 years, we've been talking about the front-end transistors. That's what is shown here as silicon CMOS. Then we talk about the back end of the line wiring, and of course we talk about the package. And so each of these areas has been individually developed, and then we have figured out a way to basically combine them, put them all together. So whether it be in the form of an EDA flow or through technology development itself, basically we have glued them together. Right? And as a result of that, there has always been this interface between what happened inside of the IC and what happened outside of the IC that still remains a bottleneck. So the thinking here moving forward is to figure out a way by which you can create these Lego blocks where you can seamlessly connect them together, both in 2D form as well as going vertically up in 3D form, such that you can combine this monolithic and package scaling, right? And such that you have vanishing interfaces between ICs. So you don't want to be able to slow down the signal just because it's going from inside of the chip to outside of the chip. You want to keep that performance at the same level. And all of us are familiar with the electronic side of things. Photonics, we believe, is going to play a very, very important role. And I think that's what Shankar Basu was talking about this morning. And he was talking about applying machine learning for photonics integration as well. So a starting point, this is what Paul was referring to. So we have a center called CAML. It's an NSF center joined with NC State, Illinois, and Georgia Tech, where we've been looking at elements of this problem over the last 5 years. And the idea here is that we told ourselves when it comes to a lot of these microelectronic systems, you're invariably looking at these very large design spaces where you have to look at some of the multi-physics issues related to it. And what I mean by multi-physics is the thermal aspect of the problem, the mechanical aspect of the problem, electrical, and so on and so forth. And with these design spaces being very large, it becomes very, very challenging to be able to simulate the performance of a lot of these structures before we can actually design them. Right? And you have a host of tools that are listed over here. And the second problem is, if you're trying to do optimization, you're relying on these simulators. And if these simulators are slow to begin with, that doesn't help at all. Right? So therefore, the logic here was, why not start looking into a machine learning environment that where you can learn from these slow simulators, create these fast models, and do design and optimization. So that was the logic here. And that's what I call here as rethinking the design process, but with a focus on heterogeneous integration and system scale. So let me try to expand on that. So what is the problem really? So if you look at a lot of work that we do, which lies at the interface between the IC and the package itself, we go through a design process that requires a huge amount of human intervention. And a lot of it is spent on trying to explore design spaces and trying to do optimization. And I think this was touched on many times by several of the previous speakers. So the idea here is there a way by which we can introduce machine learning into this kind of a flow such that we don't have to keep going through these loops over and over again, where the human can probably spend more time on more interesting problems as opposed to doing a lot of these very mundane things. Right? And so question is, how do you go about doing that? And that's where rethinking design and optimization comes in. And I think there are a few very important areas to address here. One is addressing these very large design spaces. And oftentimes we get into high dimensional problems. I think this was brought up by the previous speaker. Same applies over here as well. And computing a lot of these probabilities becomes practically intractable. And so one of the approaches by which one can address something like this is by using this Bayesian learning. And the second is this addressing optimization. And once again, I think this whole issue of why not use intelligent sampling, I think this was brought up during the panel discussion. Why not use intelligent sampling as a way for us to figure out how to do optimization? One can actually do that by making use of this Bayesian learning. That's number two. And the third is, and I think this was brought up in one of the discussions as well, when you're making these predictions and inferences, how do you know that there is no error around these predictions? So establishing confidence bounds, what we call as uncertainty quantification, becomes very, very important. So I know there have been a lot of talks on using reinforcement learning as a way to do optimization. So here I would like to propose this Bayesian optimization as another way by which one can do that. And I think there were a few presentations in that area as well. So I want to start with some history, and the reason for that is the other issue that was raised during the panel discussion is we need to bring science into a lot of the ML related work that we do. And I think it's important to understand the history behind a lot of what we do and then bring science as part of that as well. And I'm sure all of us are familiar with Bayes' theorem, but there's a very big history around it, and those of you who are interested can read this reference at the bottom. It's a very interesting read. And you know, a lot of the work that was done, you know, in the 1700s, 1800s, all came based on this Bayes' theorem. And in fact, if you look at Alan Turing breaking the Enigma code, it was based on the Bayes' theorem as well. And if you look at Bayes' theorem, it's based on subjective as opposed to objective probabilities. And once again, if you go through the history, one of the real challenges at the time was a lot of these solutions had to be done analytically. And today, with all these powerful computers and machine learning, maybe there is a way by which you can combine Bayes' theorem with the the computing power that we have, and that's what we call as this Bayesian learning. So how does this Bayesian learning work? So we call this as Bayesian active learning, and it translates to doing intelligent sampling. So we start with a single sample, that's what is shown as initial data, and then we go through this loop. And by going through this loop, either you can pose this problem as an optimization problem, or just as a model development problem. So either one is probably you should make predictions or try to converge towards a global optimum. And if you look at this technique itself, what it allows you to do is you can take a hard problem, that's what is shown over here, where let's say that the source of data is this very slow simulator. So trying to create each sample takes a humongous amount of time. Rather than trying to do optimization based on that, we just transform this into a series of easier problems you can solve by making use of these acquisition functions and the surrogate model. Right? So that's what is illustrated at the bottom. So if you're looking at it from an optimization standpoint, you're continuously sampling the most probable and promising point to be able to converge to that global optimum. So we have been working on this for some time, and some progress has been made. And three of the algorithms are shown over here that we developed through this center that I mentioned earlier. So the first is called two-stage Bayesian optimization, TSBO. And what is unique about this is it learns acquisition function. So you don't have to define what that acquisition function is. And it uses this 1D tree, so you don't have to do optimization of the acquisition function. And the typical dimensionality of the problem we can solve there is roughly of the order of around 15. And we went one step further. We developed this other technique called deep partitioning tree Bayesian optimization, or DPTBO. And what it does is it replaces the 1D tree search with a 2D tree search when it comes to optimization of the acquisition functions. And we use this additive Gaussian process to be able to increase the dimensionality and the accuracy. The dimensionality takes us to around 50 or even more. Right? And one can argue maybe you need to scale it to higher dimensions. And there are ways by which one can do that I will not address today. And the third one is this Bayesian active learning with dropout. And what that allows you to do is not only do optimization, but also do the prediction with an uncertainty quantification around it, basically establishing confidence bounds. And all of these are available as open source through GitHub. So you can download it, the link is provided over here. So let me just show you some examples of the work that we have done. So one is in the area of clock skew minimization. There was a presentation earlier today by Rishikesh trying to look at thermal simulations. This is extremely important. So here we're looking at a stack of 3 ICs where the center IC, let's say, has a clock tree, and you're trying to minimize the thermal gradient on that chip based on the heat map that is being generated by the chip above and the chip below, which are basically logic chips, and that's what is shown as a temperature profile over here. And the idea here is, how do you tune a lot of these package parameters, for example, the speed of the fan, the kind of thermal interface material you're trying to make use of, and things like that, to be able to converge towards the minimum clock skew. And if you look at the convergence itself, what you see over here is a typical ML-based optimization technique, the Bayesian optimization method, and you can do much better than that based on the data that you're working with, and that's what is shown through this curve over here. And most of these Bayesian optimization methods tend to do much better compared to other types of non-ML based techniques. Here is an example where it's been compared with a non-linear cell. Another example is this RF wireless power transfer system. Here the dimensionality is upwards of around 30, and here you can basically tweak the layout that you have over here, the coil area, as well as try to tweak the other circuit parameters. And here your goal is to be able to maximize the system efficiency, because you're trying to do RF to DC conversion over here. And once again, if you look at this DPTBO, you begin to see a lot of advantages, almost 60% efficiency, because most of the time with all of these RF to DC power transfer system, the efficiencies are of the order of around 30 to 40% or so. You can do much better than that. And what is typical with a lot of these optimization techniques that are ML-based is this very fast convergence you get in just a few iterations, that you roughly know where the optimum value is. The third is in the area of high-speed channel signaling. So here you're trying to communicate between chips at a very high speed. And if you look at this graph here, what is shown are the validation cases, basically the test cases. The vertical axis represents the horizontal eye opening. And you have two curves on top of each other. One is a blue curve, which is the actual, the truth. And then you have a red curve, which is the prediction. And then there is the shaded area around the red curve. That's the confidence bound. So basically, when we make predictions, you can also bound or provide uncertainties around the predictions coming from things like the parameter tuning, the lack of data, and things of that nature. You can capture all of that so that, assuming you feel that the confidence bound is too large, you can allow these algorithms to run for a few more iterations so that you get a better convergence. The next example is beamforming for 6G communications, and the idea here is you want to be able to tune these parameters for these phase shifters such that you can maximize the amount of power along the main beam as opposed to a lot of the side lobes. And you can do that quite well again. So if you look at this figure here, that is the main beam, and you have several techniques that are compared over here. And with this Bayesian optimization technique, you can maximize the amount of power going towards the main beam direction. Now we've also gone one step further, and the thinking here is, obviously when you're trying to do different types of packages, there are different package architectures you can come up with. And this is an example for inverters for EVs. And if you look at a lot of the chips here, how much time do I have for? Okay, thanks. So if you look at EVs, there's a trend towards using silicon carbide types of chips. And packaging is once again plays a very important role where you're looking at 3D package architectures, integrated cooling solutions, material innovations, and things like that, where you're looking at different types of multi-physics simulations to be able to do co-design. So once again, you can pose the problem in a slightly different way, where you can bring in these categorical variables, where you say that one of the variables that I have is the package architecture itself. So you see a U-shaped architecture, there is a different architecture over there, so you can bring input different types of parameters associated with each one of these architectures to figure out what that optimum solution is going to be. And by doing that, you can create your Pareto fund where you can come up with different types of solutions and figure out what actually works for you. So in this particular case, you can come up with a solution where the overall package volume gets reduced by almost 70% just by going through this optimization process. So let me skip a few slides over here since I'm out of time. So let me just get to this one. So what you can also do, and this is a little bit different type of a problem, is when we do training and when we do predictions, we always do predictions inside of the design space over which we have trained the model. But there are ways by which you can extrapolate outside of that space as well, and this is an example of a power delivery problem, looking at it more from a packaging standpoint. So if you look at this particular example, the training occurred over this frequency range, and using that same trained model, we are trying to predict what happens outside of that training space. And you can do that along with quantifying uncertainties around it, shown as in the shaded area over here. The whole point here is reduce the amount of time it takes for you to go through the design process itself. So with that, let me summarize. And what I tried to cover today is primarily on the optimization on the uncertainty quantification side. There is also an area that we're working on inverse design that Ulu Vashe is going to be presenting shortly. So I'm not going to cover that today. But let me just conclude with this one slide. I think this is very important. And there are so many problems that one needs to tackle moving forward. And a lot of it is EDA related. And in many of the presentations yesterday and today, there was a lot of talk about PPA. Right? So power performance, right? Absolutely. When it comes to area, it's no longer just about area, it's about form factor. Right? So it's a combination of area as well as the vertical height. It's more volumetric as opposed to just area. Cost is going to be a very, very important metric moving forward, and reliability. So it is now going to be PPFCR moving forward, not PPA. So with that, let me conclude here, and thank you so much for listening.